Refraction through a prism. When a light ray is incident on a prism, we know that it undergoes deviation. When white light is incident on the prism, then it undergoes dispersion. It will be divided into its constant colors. A white ray incident on a prism will be divided into its constant colors. If these constant colors they are brought and they are caught on a screen, colored patches will be formed known as spectrum. If we notice the colors, violet will be near the base of the prism, which will have the highest deviation, and red will be nearer to the incident ray direction and its deviation is least. The deviations of other colors will be in the order of VGR. So the deviation is highest for violet and least for red. We know that the wavelength of red is highest and the wavelength of violet is least. When we come to the deviations, we notice the deviations. Now we will go to the refractive index. The refractive index depends on the deviation. If the deviation is highest, the refractive index is highest. If deviation is least, the refractive index is least. So the refractive index is highest for violet and it is least for red. When we analyze the focal length of a lens in terms of the deviations, in terms of the rays, monochromatic rays, the focal length of a given lens depends on the color of light used. If violet light is used, the focal length will be less, and if a red color is used, the focal length will be more. So a lens will have focal length depending on the color we have used. For red color, its focal length is highest, and for violet color, its focal length is least. When we come to the speed of light in a medium, it depends on the color. It depends on refractive index. If refractive index is more, the speed is less. So the speed of light in a medium is less for violet color and it is more for red color. And dispersion. What is meant by dispersion? A ray of white light passing through a prism splits up into its constant colors, namely VGR. A ray of white light passing through a prism splits up into its constant colors, VGR. This phenomenon is called dispersion. The material of the prism is called dispersive material. The material is dispersive material. We have already studied the deviations. Sometimes deviation takes place along with dispersion. Both deviation and dispersion will take place. Red with highest wavelength will have the least deviation. Violet with least wavelength will have highest deviation. And the refractive index is highest for violet and least for red. These things we have just studied. Now let us proceed to study the dispersion mathematically. To study dispersion mathematically, let us consider two rays. I am here choosing red and violet. First, let us recollect what is meant by angle of deviation. Angle of deviation is the angle between the incident ray direction and the emergent ray direction. So the angle between the incident ray direction and the red ray direction is dr. It is indicated with dr name. That means it is angle of deviation for red color. Similarly, the angle between the incident ray direction and emergent violet ray direction is indicated with dV, that is deviation of violet radiation. The difference dV minus dr, is a measure of the angular dispersion. It is a measure of the angular dispersion. A quantity used for determining the dispersive power of the material. A quantity used, dV minus dr is a quantity used for the determining the dispersive power of the material. There is another quantity which is used for measuring the dispersion, known as dispersive power. Dispersive power omega is defined by the relation omega is equal to dV minus dr by dy. dV minus dr by dy is termed as dispersive power. It is a measure of the dispersion of a prism. It is a property of the material. Here dy represents the deviation of yellow color. Its value will be the average of dV and dr. That is why yellow is chosen. Spectrum. The emerging dispersed colors, when caught on a white background, white screen, they form colored patches called spectrum. So spectrum is that which is formed on a white background by the dispersed colors. We observe overlapping of the colors when a spectrum is formed by the dispersion of a prism. The dispersed spectrum, it will be overlap. That means one color gets mixed with another color. The colors get overlapped. Such a spectrum is called as impure spectrum. Impure spectrum. If the colors can be arranged clearly one after the other without overlapping, such a spectrum is known as pure spectrum. A spectrum in which the colors are spread out with clear distinction without overlapping is called a pure spectrum. Here, a pure spectrum is given here. There are certain conditions that are to be fulfilled to obtain a pure spectrum. Some arrangements must be made in order to get a pure spectrum. The conditions that are to be fulfilled for obtaining a pure spectrum are a narrow beam of light, a parallel beam of light, the prism should be kept in minimum deviation position, a converging lens that focuses different colors to different positions on the screen should be used. So these are the conditions: a narrow beam of light, a parallel beam of light, prism in minimum deviation position, and a converging lens which focuses the emerging. The conditions required for pure spectrum are provided in a device known as spectrometer. In spectrometer, the conditions required for a pure spectrum are provided. A narrow beam is provided by using a slit. In slit there will be two plates. If the separation between the plates is decreased, then we will get a narrow beam of light. So here in this figure, S is source, SL represents the slit, which gives out a narrow beam of light. This beam, it is made to fall on a lens known as collimating lens, L1. This lens is so placed that the slit will be at its focus. When an object is placed at the focus, the emergent rays will be parallel. So the slit will be placed at the focus of the lens L1. The emergent beam is parallel beam. So the second condition, a parallel beam, is obtained here. ABC is a prism. It will be kept on a prism table. The prism table can be rotated to any direction, to the desired direction. By observing the emergent rays, the prism table will be rotated. Then we notice the deviation to be decreasing. At one stage, the minimum deviation will be attained. At that position, the prism will be kept constant. Then there will be a lens, convex lens in the telescope, which is used for converging the rays, different color rays, to different positions. Now, these are the arrangements that are provided in a spectrometer. Collimator and slit, they will be placed in collimator. Collimating lens, I mean. Collimating lens and slit, they are kept in collimator. And this converging lens, L2, it will be placed in the telescope, in which there will be eyepiece, which is used to observe the spectrum. To understand the colors in a spectrum, to understand the different colors in a spectrum, that is the lines, colored lines that are responsible for the spectrum, colored spectrum, we need to understand the mechanism in which photons are emitted. We need to understand the mechanism in which photons are emitted. For this purpose, we have to study about excited atoms. If an electron in an atom occupies higher energetic level, it is called an excited atom. It is called an excited atom. Excited state of an atom can be obtained from one of the following ways. Excited state of an atom can be obtained from one of the following ways. By heating a substance in a Bunsen burner flame, by introducing the substance in an electric arc, or in an electric discharge through gases. By producing an electric arc between two metallic electrodes. Another way is by producing an electric arc between metallic electrodes. In an atom, the energy levels are discrete and their separation is large. When we consider a single atom in which the electrons are situated in different orbits, the energy difference of these levels is much higher, very large. When a molecule is formed by 2 or 3 more atoms, the energy levels will increase, and thereby the separation of the energy levels will become very less. A single energy level split up into number of energy levels when a molecule is formed. So the energy difference between two levels becomes very, very small when the molecule is formed. Let us study the formation of a spectrum, different colored lines in a spectrum. The energy of a photon depends on the difference of energy between the transition levels. The energy of the photon depends on the difference of the levels of energy between which transition is taking place. Here I have assumed the numbers, the energy levels as 1, 2, 3, 4 from outside. I have given the 1 for the outermost orbit. Generally we will give them from inside. So according to this figure, the transition from 1 to 4 gives 1 photon. The transition from 1 to 3 gives another photon. The transition 1 to 2 gives another photon. The energy of the photon emitted when the transition takes place from 1 to 4 is much higher compared to 1 to 3 transition. The photon of 1, 2, 3 transition will have more energy compared to the photon of the transition of 1, 2, 2. Similarly, the other transitions. There are 2 to 4, 2 to 3, 3 to 4, etc. Like this, there will be several transitions between energy levels. So 1 to 4 transition photons, all these photons, they constitute one colored spectral line. 1, 2, 3 transition photons, all these photons, they constitute one spectral line, one colored spectral line. Like this, each photons emitted from each transition, they will have a particular energy level. So they produce a line of particular color. So in this case, 4 spectral lines will be formed if the electron in the hydrogen atom is initially in the third excited state. Here we notice 6, but in the case of hydrogen atom, if it is in the third excited state, then 4 transitions are possible. Line spectrum. In line spectrum, we notice discrete spectral lines, colored lines with dark spaces in between. One line spectrum is formed if the transition is only between one pair of levels. One line spectrum is formed if the transition is only between one pair of levels. In the previous case, we have seen 6 transitions are likely. So 6 lines are likely to be formed. In the previous case, we have seen 6 transitions. So we notice 6 spectral lines. The position of the spectral lines depends on the wavelength of the radiation emitted due to the electron transition. The photon, it is associated with some wavelength. Though the energy is emitted in the form of a photon energy packet, it will have a certain spectral line, certain wavelength. For example, if the electron transition takes place from energy level E2 to energy level E1, the transition may take place between E2 to E1. In such a case, the wavelength of the radiation emitted is given by the following relation. E2 minus E1 is the difference in energy between the two levels. That will be equal to hc by lambda, where h is Planck's constant, c is speed of light, and lambda is wavelength of the radiation. So between two energy levels of energy E2 and E1, if the electron transition takes place, the wavelength of the radiation emitted is given by the relation E2 minus E1 is equal to hc by lambda. From this type of relations, we can determine the wavelength of the radiation emitted. So line spectra are formed if the substance is heated in the form of atoms. If the substance can be divided into the form of atoms and heated, then line spectra will be formed. Generally, line spectra are formed from vapors of lamps, sparks, and by discharge phenomena. Line spectra, the procedures, the methods of producing line spectra are vapor lamps, sparks, and by discharge phenomena. The methods by which these spectral lines are produced are by heating a substance to incandescent state, by burning a substance in Bunsen burner flame, by creating an electric arc between two electrodes. Another type of spectra are known as band spectra. Band spectra. Here we notice 3 bands. Band spectra consists of colored bands intercepted by dark spaces. Band spectra consists of colored bands intercepted by dark spaces. Each band is composed of several closely spaced spectral lines. Each band is composed of several lines, very closely spaced spectral lines. The lines are very close at one end, and we call this end as band head. At one end, they are very closely spaced. The spacing of these lines increases as we proceed towards the other end. So from left to right, when you notice the spectral lines distances increase. These spectra are formed by the energy emitted by molecules. When matter is heated in the form of molecules, band spectra are formed. In a molecule, the vibrational and rotational energy states are also quantized. In a molecule will be having vibrational energy and rotational energy. Vibrational energy states and rotational energy states are quantized. So the energy difference is very small between adjacent states. Between adjacent states of vibrational states or between adjacent states of rotational states, the energy difference is very, very small. When the transition takes place between these closely spaced energy levels, the difference in wavelength will be very, very small. So closely spaced spectral lines are formed. Closely spaced spectral lines are formed. That means the wavelengths are very, very close. This is due to the closeness of the energies of these photons. It is due to the transition of the molecules between superfine energy states, that is very, very closely spaced energy levels. Continuous spectrum. Continuous spectrum. Continuous spectrum consists of all the colors in WebGR. Continuous spectrum consists of all the colors in WebGR, and there will be no dark spaces in between. There will be no dark spaces in between these colors. The colors merge with their neighbors. The colors merge with their neighbors and mixed colors will be formed in between. When the matter is formed in the form of molecules, hybridization of energy levels takes place. Energy levels split up into large number of energy levels. One energy level split up into large number of energy levels, that is known as hybridization of energy levels. If the molecules, they form either they come to the liquid state or gaseous state. When the molecules become a liquid or a solid, the energy levels will become very, very close. So the spectral lines, the wavelengths of these spectral lines is so close that we cannot distinguish them. So the lines, they appear to be mixed with one another. The separation between these lines is not apparent. So they appear as a single color. So we notice a continuous color instead of spectral lines. Continuous spectra are formed, they are emitted by incandescent solids and liquids. Incandescent solids and liquids, they produce continuous spectra. Absorption spectra. Absorption spectra. An atom placed in the path of white light. An atom placed in the path of white light absorbs its characteristic color, and the result is a dark line in place of bright line. In place of bright line, we notice a dark line if an atom is placed in the path of white light. Emission spectra are formed when the transition takes place from higher energy level to lower energy level. But by absorbing energy, the electron goes to higher energy level when the atom is placed in the path of white light. By absorbing energy, the electron goes to higher energy level when an atom is placed in the path of white light. So this is the reverse process of the emission spectra. So the electron absorbs energy from the white light. If you form the emission spectra of sodium, when sodium is heated in Bunsen Bunsen burner flame, you notice two bright yellow lines. Two bright yellow lines. If the same sodium is placed in the path of white light, if the same sodium is placed in the path of white light, you notice two dark lines in the place of bright lights. So, in absorption spectra of yellow, we notice two dark lines in place of bright lines. A substance absorbs the same radiation that is emitted by it when it is very hot. The substance absorbs the same radiation when it is placed in the path of white light that it is emitted when it is very hot. The substance absorbs the same radiation when placed in the path of white light that it has emitted when it was very hot. So, absorption spectra consists of dark lines. If you take sunlight, analyze sunlight, you notice continuous spectrum. Across the continuous spectrum, you notice dark lines. They are known as Fraunhofer lines. So, they are absorption spectra.